Guys, welcome to the level 2 physics 2020 waves paper. I'm just going to go through the questions. I don't have a marking schedule, so these might be wrong, but yeah, just let me know in the comments if you think you have a different answer to me. Okay, question 1. At the swimming pool, Maya and Arya at the swimming pool, they notice the lifeguards are using convex mirror in the wall to help them see the swimmers in the pool. Complete the ray diagram. Okay, so convex mirror, a line from here to here, and it's going to go out from here like here, but then this is actually going to be dotted. It's going to be like this, and we can do one straight to the pole like this, and it goes through here. And we can do another one, and we can do a line that goes towards the focal point like here, but it's gonna, from here it's gonna reflect parallel to the principal axis. So here we go, here's our image. Okay, this is not the best diagram, but you get the idea. Determine the nature, size, and orientation of the images of the swimmers formed by the mirror. Assume the mirror is far away from the swimmers, so I'm guessing that it's outside the, what they mean by that is that that object is outside of focal length. So it's going to be virtual, upright, and diminished. You can see that it's upright and diminished, and upright images are virtual, and for convex mirrors the focal point is negative, or focus point, so it's going to be a virtual image. The lifeguards could have used a plane or concave mirror. By describing the possible images from each mirror, explain whether either mirror is suitable for the lifeguards to see the whole of the pool. So a concave mirror is going to give us an image that is inverted, real and inverted. So we probably won't want to use that in a pool, because a plane mirror will just give us a laterally inverted image. What else can we say? So the plane mirror is going to be the same magnification. I'm not really going to write this in detail, I'm just getting the main points. Plane mirror gives, what can I say? Same scale image, whereas a concave is going to give an enlarged image. So you can just write down these points and then write why a plane mirror would be better, because obviously you don't want a concave mirror because it's going to be enlarged and it's going to be inverted, so you don't want that in a pool. But a plane mirror will show you the same, whatever you're seeing in the mirror is like the same scale. So yeah. Question D. The children's play pool has a small partition with a large convex lens built into it to create patterns in the water. Y is 1.7. So HO equals 1.7. DO equals 2 meters away from the lens, which has a focal length of 0.5. Calculate distance of image. Okay, so we just use our formula 1 over f equals 1 over di plus 1 over do, which is going to be... we can rearrange this equation to make di the subject, so di will equal 1 over f minus 1 over do to the power of -1. And when you plug in your values, you should get your distance. Okay, I'm just going to do that. di equals 1 over 0.5 minus 1 over, what is it, do2? 1. And this equals 0.6. Okay, how much sig figs? Oh, sorry. So it's going to equal 0.6667. How much significant figures do they want? They want, here we got 3, 3, 3. Okay, so 3 significant figures. So this is going to be 0.667. And it was in meters. Okay. Calculate the height of an image. So height of image is going to be hi over ho equals di over do. So hi equals ho times di over do. This is going to equal ho 1.7 times di, which is 0.667 over 2, which gives us 0.567, and that's meters. Okay. And that was 3 significant figures, because all these values here were 3 significant figures. Describe the nature, size, and orientation of your image. So, when we have a concave mirror, convex lens, not a concave mirror. So we have a convex lens, something like this. And let's say we have object here, focal point here. We are going to get, the rays are going to go from here to here, and it's going to go from here to here. So the image is going to be so that is inverted. We can clearly see it's inverted, and it's a real image, and it is diminished. Inverted, real, and diminished. We can see from this diagram here. You don't need to draw this, but it just helps. Question 2. The bottom of the pool. Aria sees an object on the bottom of the pool at the shallow end and reaches down to grab it. She finds the object is actually deeper than it looked to be. Okay, so that will be refraction, I believe. Hopefully, because that's what I did. The formation of the image. Okay, so we know that. So this is going to give out rays, like, let's say from here. And this is going to refract to our eyes. But our eyes can't actually see this refraction, so we're just going to think that the image is like over here. Something like that. So, yeah. I think they're meant to be dotted lines, like the lines would need to be dotted over here, but anyway. Use physics principles to give a full explanation of how the process in part B causes the observer to see the image at the position located by a diagram. Okay, so what we can say is, I'm not going to go too in depth, I'm not going to write it that good, but I'm going to try to cover as much as I can. So we know that a change in mediums causes rays to bend. So in this case, the change in mediums at the air-water interface. Hang on, I'm just going to try something. Okay, no, that's not going to work. Sorry. To the air-water interface, at the air-water interface, causes the rays to bend or refract as it is going from a denser medium to a, what could I say, less optically dense medium. Since it's going from a dense medium, which is the water here, this is the dense medium, and this is a less optically dense medium here. So since it's going from here, it is going to, so there's a normal line. It will bend away from the normal. Yeah, so the ray will bend away from the normal. The ray will bend away. This is really messy, but I'm sorry. The ray will bend away from the normal. Our brain cannot backtrace or take this refraction into account. I don't really know if that makes sense, but oh well. Cannot take this refraction into account. So the rays are backtraced in a straight path. Hence the image, okay, something has happened. Okay. But, okay, it's disappeared, but I'll just write it again. So the rays are, going to be back traced in a straight path. Hence, object appears closer. So what this means is that when the rays are going for like this dense medium, like water to air, this is the normal line. It's going to bend away from the normal line. So instead of like here, it's going to go this way. And our brain, so this is this ray here, this is that ray, and it refracts down here, right, to where the object is. But our brain can't our brain doesn't know that this refraction is happening, so it'll just think that it's over here on this straight path. So the image it'll think the object is here, and you just write about that over here. Anyway, question D. Mai jumps into the deep end and looks up and sees the bottom of the pool reflected above her, as shown below. Okay, yeah, it would be good if there was a photo, but oh well. Okay, so I found the image. Okay. Yeah. So that is the image that was in the exam. I've just put it in. So identify the phenomenon that is taking place. So the phenomenon that is taking place is total internal reflection, not total internal refraction. So total internal reflection. Write a comprehensive explanation of how this phenomenon occurs. Include the conditions required and the calculation of the critical angle. So I'm not... Yeah, okay, so I'll just tell you the main points. So the conditions required, that is going to be the angle of incidence has to be greater than critical angle. And this is true for a ray going from a from an optically dense medium to a lower optically dense medium, I guess, called density. Yeah, so those are the two conditions for total internal reflection to occur, and they want a calculation of the critical angle, so it's going to be it's going to be N1 sine 90 equals N2, what am I doing? N2 sine critical, theta critical, so N1, 1 and 1.33, so this is going to be 1 sine 90. I'm hoping this is right. If you think it's wrong, just let me know in the comments below. 1.33 sine. So this is going to be inverse sine 1 over 1.33 equals critical angle. And this is going to give us... Sorry guys. So this gives us a critical angle of 48.75, so 49, what am I doing? 49 degrees. Yeah. Question 3, the wave machine. There's a third pool with a wave machine. The pool has a deep and shallow end. The wave machine generates waves with a period of 2.3 seconds. So t equals 2.3. The speed of the waves equals 2.75. Calculate the wavelength. So f equals to 1 over t and v equals to f over wavelength. So calculating frequency first. Frequency will be 1 divided by 2.3, which gives us 1 divided by 2.3, 0.435. Again, let me know in the comments if you think this is wrong, because I think it's wrong. I don't know why. Hertz. So wavelength equals to V over F. So wavelength equals to 2.75 over 0.435. So 2.75 over 4 equals, this gives us 6.325 meters wavelength. Okay, the waves move from the deep end to the shallow end. Complete the figure below to show the effect of the change on depth on the appearance of the wavefront. So it's just, I think it's just going to move closer. That's it. Frequency remains the same. So wavelength decreases, and I don't think it refracts or like bends. I don't think like the angle would change. I hope not, because this is what I did in the exam. Anyway, use your diagram to describe and explain how the wavelength, amplitude, and frequency. Okay, so this one I'm not too sure about, but I'll just say what I think it is. Okay, so wavelength decreases and amplitude increases. Wavelength, amplitude, frequency is the same. Yeah, so these are like the main points, I guess, I think. So you would just want to, write it properly. Moving on to question C. On one side of the pool there are 2 lights, and on the other side of the pool there are 2 speakers. Describe and explain the differences between the waves emitted by the lights. So the waves, so that'll be the type of wave emitted. Yep, answer should include a comparison of the wave type, need for a medium, and the speed of the waves. Okay, so light is a transverse. What the hell? Light is a transverse wave, whereas sound is a longitudinal wave. So that's the type of waves. I'm not going to write it out, I'm just covering like the main points. The need for a medium. So sound has a speed of 0 meters per second in space. In other words, a vacuum. Therefore, it needs a medium to propagate, I think. That's what we would write. So, because sound waves, let's say this is a speaker here, they like push forward air particles, and then those air particles then come back. So the air particles are like vibrating, I guess, back and forth. And in space, there's no, like in a vacuum, there's no air particles. So there's no air particles for it to like vibrate. So there'll be no sound. So there needs to be a medium for sound to be heard, I guess. And light changes speeds depending on the medium. It changes speed and direction too, I believe. I'm not too sure. So it'll change. Light changes speed and direction on change in medium. Okay. Question D. During a test of the evacuation siren, a sound of constant frequency is emitted continuously from both speakers. So, two speakers. A lifeguard walks along the pool from the opposite side. Let's say he walks from here to here. From point A to B, let's just say. And use physics principles to explain and justify what the lifeguard would hear. Okay, so two speakers. This comes every year, these questions. So there's going to be constructive interference and destructive interference. What can I say? Okay, so as the lifeguard moves across line B, I can say, or moves past speakers, he will hear loud and soft spots of sound. So at some points it's going to be quiet, and at some points it's going to be loud as he walks along here, because at some points there's like constructive interference and destructive interference. Okay. Yeah, so it'll be loud. Sound will be louder at points where constructive interference occurs. At these points, the waves are in phase. Antinodal points are formed. What else? Crest and trough. I think we can say that this is where the crest and crest or trough and trough meet. I think we can say that too. And also what we can say is there is a path difference of, I think it's, this is how you write it. No, not half, that's for the other one. So equals n wavelength, that's the path difference. I think that is how you write it, but you do want path difference for both of them. So yeah, that's the where it's going to be louder. Sound will be quieter where the waves are undergoing destructive interference at these points. The waves are out of phase. What did I say here? Waves are out of phase. Oh yeah, nodal points are formed. Nodal points formed I'm just going to carry on to here. Nodal points are formed. What else can we say? I'm not too sure if we can write this, but this is where crest and trough meet. Because where crest and... oh, what is this? Okay. Because where crest and trough will meet, if it's like this, then they'll add and they're going to cancel out to produce like a straight line. But where if you have like a crest adding with another crest, like this is coming that way, this is coming that way, then they're just going to add to make it larger. So yeah, what else can we say? Nodal point formed. Okay, and over here, for where the sounds are quieter, where there's destructive interference, the word path difference of n plus half wavelength. I think that is how you write it for the destructive interference path difference. And that's it, guys. Thanks for watching. Like, share, let me know in the comments if you think the answers are wrong or different, or if you think just anything. Just let me know in the comments below. Thanks for watching. Good luck with your future exams if you have any.